All right, we're going to get going with the next lecture. Erik Wallace, who is a postdoc here at UConn, is going to talk about elliptic curves over finite field.
All right, thank you. Can everyone hear me fine? All right. So I've written some notes for you. They're available online. I have on the first page some references from outside of the notes that I use for preparing them. And, you know, the thing is, of course, my favorite reference for elliptic curve cryptography is the one at the bottom, the Safe Curves website. But it is very dense and hard to understand. And so part of the goal of this, of the notes and of my lectures are to try and unpack what he has there on that website. And the other resources are very helpful in doing this. And there are, you will note that at the end of each section, there are exercises for you to do. I may not be going over this, I will not be going over the sections in the same order. The first two sections are kind of going to be discussed on the fly. I'm basically skipping over them and going over them on the fly as I need them. And other details in there may drop out completely because they're much longer in detail than I have time to discuss in these short talks. So I encourage you to read them if you can. If you want to give me feedback to improve them, I would appreciate it. There are also a couple problems at the end, which are sort of computational problems that are longer than the exercises, and they actually tie in pretty well with even some of what Alvaro is doing. You can look at them from a sort of statistical probability theory perspective. Let me show you that page. It's the last page of the problems. So I so far only have two problems posted. The first one concerns rank and its connection with elliptic curve cryptography. People have asked me about this, and I've never really had a good answer for them. And so this problem is intended to sort of investigate that and see if there's actually something there or if there's really nothing we have to worry about. And the second problem, but otherwise I'm generally not going to be discussing rank. For the most part, rank is not part of these talks. But the second one is closely related to the sorts of safe curves that you see on the Safe Curves website and how to construct them. And so there's sort of this idea of what might be optimal, and so there's questions about whether we can do even better than the ones on his website. And in terms of how common they are, there is a connection to the Goldbach conjecture and to Sophie Germain primes, it would seem. And so we have asymptotics for both of those, and they're pretty promising, and so one would expect reasonably many examples so that they're relatively easy to find. But the question is, how can they be found efficiently? And so this problem actually breaks down the issues to try and sort out the details and see if there's certain things that can be looked at earlier than others to weed out bad cases and make it more efficient to find them. That's the main goal of this, of that problem. So that is all I want to show you from the PDF notes right now. And concerning SAGE and magma, I know Harris is mainly going to be discussing magma. There are SAGE examples in my notes. I may even discuss SAGE code a little bit in these lectures. Magma's biggest advantage is its speed. Absolutely, it's faster than SAGE. But I don't like most other things about it. SAGE is free. It's Still a little bit quirky sometimes, but in my opinion, not as quirky as Magma. If you are at least a Mac or Linux user, there is no problem installing it. If you are a Windows user, unfortunately, your options are installing it in VirtualBox or using their online version. They have an online version like Magma. It used to be called Sage Math Cloud. They switched the name to CoCalc. But it is basically an online version of Sage. But if you are a Windows user and want it on your laptop, I can help you get it on your laptop. I have done it before. Okay, so let's start here. I'll hopefully. So first of all, let's see. Is this? Let's see if this is big enough. All right, so it's like that. I guess I should zoom out a little bit, maybe, so you can see. All right, and maybe also since it's better it's orientation. Okay, so elliptic curves. So for the most part, we're going to be dealing with many kinds of different equations, but for the most part, the simplest examples of elliptic curves, the classical examples, come from the form where you have y squared equal to a cubic polynomial. You might also want to assume that the roots of the cubic are distinct, otherwise you're not going to get an elliptic curve. And so how do they look? Well, if you draw the curve in the real part of the plane, consider this, say, over the complex numbers or over a finite field or some other field. But if you're doing it over the real numbers, you might get something like this. With two pieces, and each one of these points here with the intersection of the x-axis is corresponding to a root of that cubic polynomial, right? Because that's where the y-coordinate is 0, so you've just got the cubic equal to 0. So if you have three real roots, you get something like this. But if you have only one real root, then you have only, say, that part or something like that. Okay? So now the whole thing with elliptic curves is you can define a group law on them. And there are, so the way you do this, there's a geometric way that's very intuitive. Okay, I'm going to draw a line here. And so these 2 points here, P and Q, are the points I want to add. And that third point there is not their sum quite. You could pick any other point on the curve as the identity element. But the standard thing is just to take a vertical line and then call this point down here. It's supposed to be symmetric across the x-axis, right? It's just, you get a plus or minus y value as your options if it's not 0. So you have P plus Q down here. And in my notes, this is called R. And R is just this auxiliary point. And where's the identity? Well, this vertical line looks like it only intersects the curve at 2 points. And generally, in math, we like to do things which define things which don't have exceptions. And so ideally, we would like to be able to say that if you give me a line and a cubic randomly, they intersect at 3 points. Period. No exceptions. No. But you need, in order to do this, you need to sort of change your rules a little bit. And one rule you need to change, of course, is dealing with tangents, right? So if you're dealing with tangents, you've got a point which is actually kind of a double intersection. And you can look at that in terms of a double root of a polynomial. You can see that in my notes. I doubt I'll have time to go over it, but if you have a polynomial that is tangent to the x-axis, say, it's going to have a double root. If it's tangent at x equals a, it's going to have x minus a as a factor twice, or even more than twice, if it's intersecting more than twice. So we have to consider the number of points of intersection being the multiplicity. But then still there's a problem with these vertical lines. And there's, so we sort of extend to points at infinity. And so this third point on this vertical line is at infinity, so to speak. And so we need to define clearly what we mean by at infinity and discuss that now. So, but that's where, so up here somewhere you have this identity element O, which is so that's the identity, and it's at infinity, so to speak. And we're going to make that concrete. But once you make these extra definitions with the multiplicity and including points at infinity, then you can state this with no exception and say that if you take a line and a cubic, they intersect at 3 points, period. No exceptions, including multiplicity and points at infinity. So that makes it very convenient. So now how do we get our hands on points at infinity? So the way I like to do it is to use capital letters for the numerator and denominator. Okay, so I'll try and make it clear when I'm doing a capital letter and when I'm doing a lowercase letter. It's easier to do, of course, when you are typing notes, but I'm going to try and make it clear by handwriting. Okay, so the trick is now I've got x and y, little x and y, represented with numerator and denominator, and I want to plug in, I want to clear the denominator. So if I plug in the x and y into this cubic, of course, and clear it, I have to multiply by the hopefully smallest power of z that gets rid of the denominator, which of course in this case is going to be 3, because I've got little x cubed. So I'll have yz squared equals x over z cubed plus a x over z squared plus b x over z plus c. And so then if I multiply through by z cubed, then I get y squared times z on this side, and then x cubed plus a x squared z plus b x z squared plus c z cubed. So that's what we call, so what we're getting at is the concept of projective geometry here. This is called a projectivization. The original equation is called an affine equation. This is called a projective equation. And it now should be clear what we mean by at infinity. We're talking about setting z equal to 0. Because you're not allowed to divide by 0, but if you take a limit as z, if you fix x and y to be, say, 1 and 2, and you take z going to 0, x and y are getting very big, right? So this is sort of intuitive in terms of that perspective. So you can think about it in terms of limits. Another thing you should see here is that I can, of course, rescale. While little x and y, I might have a unique pair, x and y corresponding to a point. That's not the case with these. I could take x over z equals r x over rz, y over z equals ry over rz for r not equal to 0, right? And I get, because the r's cancel out in the fractions, I get the same thing. And so we want this not to depend on r either. So we say that our projected points only depend up to rescaling. So if I have this triple here, okay, I'm putting colons in here for a reason. Okay, this is basically equal to, I'm going to write equal, you could write just a squiggle, similar if you wanted to, r, x, r, y, r, z, like that. They're the same point. The triple x, y, and z is not unique. You can rescale by r any way you want, so long as it's not equal to 0. And you get a different triple representing the same point. And the colons are supposed to imply this, because colon is sort of a standard notation for ratios. So really, the absolute numbers x and y and z aren't determined, but the ratio is. The ratio is unique. It doesn't change. And so that's why I use the colons. Not everyone does, but I think it's clear that way. Any questions so far on this? Yeah?
So with the two conditions you provided, those aren't sufficient to have all lines and elliptic curves intersect in 3 points, because you also need to be over algebraically close to the
right. So for now, yeah. Yeah. So for now, exactly. So for instance, even if you look at the case where I had just the one part, if I'm working only over r, then you only have one point on the x-axis there, it looks like, right? Because where are the other two? They're in the complex part. So of course, if you want, it only works over an algebraically closed field if you have all 3 points of intersection. Okay, other questions or comments? Okay, good. So we want to talk a little bit more about this line at infinity. So I said there's a line at infinity. Okay, so what happens when you have z equals 0? We have we still have the other two coordinates as options, right? But we're allowed all sorts of different things for ratios. So, for instance, I could have x be 0, right? And so that gives me one option. Of course, I can rescale the y value, but that doesn't really matter. They're all basically the same point. I get an r in there, but they're all basically equivalent, different representations of the same point. On the other hand, if x is not 0, then I can divide through by it, and I can get 1 there. And then I get some other value over here, which is could be 0 or not. But I'm writing m there because it's supposed to represent a slope. You can sort of think of it as the slope of a line. So if we go back to our picture here of the elliptic curve, I have this vertical line. It doesn't have a slope, so it's corresponding to the point 0, 1, 0. Right? It doesn't have a slope, so that has to correspond to that first point I wrote down, the 0, 1, 0 point with the 0x coordinate. And you see that that point corresponds precisely on this curve here. If you plug in z equals 0, right? If I have z equals 0 here, in this equation, what does that give me? That gives me 0 on the left-hand side. I get 0 equals x cubed, which implies x equals 0. But I'm not allowed to have all three be 0. That's another rule we have, is that x, y, z are not all, they can't all be 0. So that is the basic point there. So this is the only point on the line at infinity that intersects the elliptic curve. And since over an algebraically closed field, there are always 3 points of intersection with this cubic, that line at infinity intersects 3 times at that point. Okay, so that's pretty much automatic, that it intersects 3 times at the point in infinity. And so it's an inflection point there, if you want to think of it that way. And so that is the story with projective coordinates. And so I think that's pretty much all of what I'm going to discuss about projective coordinates in these lectures. And we're going to continue with the definition of the group law. I mean, we're going to be using projective coordinates a lot, but it's important. I'm not going to go over most of what's in that section. So for the group law, I now want to look at doubling. So of course, I said that you, if you have 2 points being the same, you've got a tangent there. So if I as an example, if I have y squared equals x cubed plus x plus 2, if I want to compute, so is it clear that this point is on the curve? You plug in 1, you get 1 plus 1 plus 2 is 4. 4 is a square. Okay, so that's a point on the curve. If we want to compute 2p in the group law, okay, you're not doubling the coordinates here. It's a geometric group law. So the first thing, of course, is you need the slope. So to get the slope, you can use implicit differentiation. So you get 2y dy over dx equals the derivative on this side, 3x squared plus 1. And you divide through by 2y. And you get that. And so then you plug in with the coordinates of your point to get the slope. So at P, we get 3 times 1 squared plus 1 over 2 times 2 equals 1. 4 over 4. It's 1. So that is the slope at that point. So now what I want to do is create the tangent line to that point. I'm not going to draw the curve yet because I don't want to give away the answer. Okay, so you can use point slope, which is my preference. It's point slope. Or you can use slope intercept. And so now we want to find the third point of intersection. So there are multiple ways of doing that. And I do it in a slightly different way in the type notes than I'm going to do it right now. So what I'm going to do here is going to do a trick where I construct a factor of y minus 2 on this side, and then using the fact that this point is on the curve, okay, that means that x minus 1 is going to be a factor on this side. Okay, so I get y squared minus 4 equals x cubed plus x minus 2. Okay, you see how I get that from here by subtracting 4 from both sides? And now this factors this y minus 2 times y plus 2. And this side may not be clear how this factors. It should be clear that 1 is a root, and so that therefore x minus 1 is a factor, but you would probably have to do polynomial division to find it. So x minus 1, I'm just going to jump the gun and tell you what the other factor is. Okay? But you find it by polynomial division. All right, and because of the fact that I have this point slope form here, which is kind of nice, I already have that these two factors are equal. In fact, I have the 1 there. The slope is 1. So I don't even get a factor of the slope showing up, which would ordinarily happen. So those just cancel. And I now have reduced the degree by 1, and I can repeat. And I can repeat with the same point because the point is a double point of intersection. If I had 2 points, I would use the other point. Okay, you just know the line intersects 3 times, so 2 of the points are known, so they tell you already some known information. You don't have to go to Cardano's cubic formula. You can just use the known information about x and y coordinates of the point to find the factorization. So that is a very useful trick. Okay, so if you once you get it in this form, okay, then you can so this you subtract 4 again from both sides. You have 1 again as a root here on this side, and this is easier to tell what the factorization is. And so that tells you the x-coordinate of the remaining point, the point R. Okay, so minus 2 is the x-coordinate of R, third point of intersection. And to get the y-coordinate, you plug back into the equation of your line. What? Sorry, I have the wrong one crossed off. Yeah, sorry. Yeah, should be... It should be 1. So this should be plus 1.
When you cancel it, you should get 1 equals x plus 2.
Yeah.
Right.
So then x is minus 1.
Yeah. X is supposed to be minus 1. Yeah. I have the wrong thing crossed off.
The break thing crossed off, it was just so that you had 1 on the left side on the 0.
Right. So right, it's supposed to. The answer is supposed to be minus 1. X is equal to minus 1. And
I think the problem is when you had there y minus 2 equals actually y plus.
yeah, it's supposed to be y plus 2.
It's supposed to be 1 minus.
Everything's fine.
I'm going to draw the picture. Okay. Okay. So this line has slope 1. Okay, and in this case, r is equal to 2p. We don't even have to reflect because the y-coordinate is 0. Okay, we actually have, okay, so there's the original point P, there's the tangent line, and it goes through there. I messed up on I wrote down the wrong thing there. Okay, so, but is it clear how the strategy goes? And of course, that's not something that you want to have to do out every time. There are general formulas which you can use, which will do the work for you to get the right point. And so those formulas are mainly what we're going to be using. But it's worth seeing this at least once to understand what the formulas do. Okay, so the original equation that we had of y squared equals a cubic is a special case. It's in a form we call Weierstrass form, and it's nice with it, the cubic on one side and y squared on the other. It really is not as general as it can be. It does not work in what we call characteristic 2 and characteristic 3. Characteristic 2 is what you have if you're in, say, z mod 2z, where if you're adding a number twice, you get 0. On characteristic 3, you're adding number 3 times, you get 0. So we're going to see why that's not such a good form in general. So the general form is this. So the Weierstrass, what we now call Weierstrass form, which Weierstrass himself never would have recognized, is this: y squared plus a1 xy plus a3 equals x cubed plus a2 x squared plus a4 x plus a6. And there are conditions on the a's for this to be actually an elliptic curve. But this equation now is valid. It gives us a way of representing elliptic curves over any field, even characteristic 2 or 3. And the one thing is, though, it's a way of representing curves. It's not the only way. So one big point I make in the section on projective coordinates and in the section on the geometry of elliptic curves is the concept of birational equivalence, what we call birational equivalence. I'm probably not going to have time to discuss that at all and what that means here in these lectures, but you will have my notes for it. The main reason you will see, hopefully at the end of this lecture, is that there are very important examples of elliptic curves in cryptography which are not in Weierstrass form. So that's why I have to bring it up. So let's see here. If we don't have characteristic 2 in characteristic, and I'm going to use the abbreviation chair K for the characteristic. Characteristic of field K not equal to 0. Right. So and K, the reason we use K for a field, in case you don't know, is from the German word Körper, which means actually body, not field. But it's the word they use to mean what we mean field. So anyway, the first step, we want to get this in the form where a cubic is on one side and a square is on the other. And so the way we can do that is by completing the square. Well, that should make it clear right away why characteristic 2 isn't allowed, because you can't complete the square in characteristic 2. And so what you get is, say, this equation, v squared equals x cubed plus b2 over 4x squared plus b4 over 2x plus b6 over 4 with powers of 2 in the denominator, making it clear that characteristic 2 is not allowed. And v here is simply what you do to complete the square. It's that. It's plus. Plus. Okay, so that is what you get from completing the square. Okay, and you can go further in characteristic 3. You can eliminate the x squared term. And this requires being able to do what we call completing the cube, which is the analogous trick. And so in chair k not equal to 3, if you take u equals x plus b2 over 12, then you get v cubed equals u cubed minus c4 over 48u minus c6 over 864. And yeah, that's not so easy to compute by hand. I mean, you can certainly do it by hand. It's probably easier once you know what you're supposed to do to get Sage or Magma to do the variable transformation for you. But of course, this has been known basically for a long time, for before we had computers. I don't think it was known quite all the way back to the 19th century because they weren't using it in this form quite so far back. But it's common. It's something that's reasonable to do by hand if you want to. Okay, and the relationship between the A's, B's, and C's, so forth. I'm going to put that here from notes I had prepared here, and you can get those by Sage or by hand or from books or other online resources. And so there's a couple important things here. The delta, the discriminant of the elliptic curve, is used to detect whether or not you have an elliptic curve. When you get 0 over whatever field you're working over, you don't have one. Okay, so 0 over the rationals or over complex numbers is not a huge deal. If you're working over characteristic P, of course, you now need to start looking for factors, prime factors. And so if you have delta being even, you don't have an elliptic curve in characteristic 2. It may work, it'll work for all sorts of other characteristics. And in fact, in the talk where it was mentioned that bad things are generally more common than good things, in this case it is the reverse. The bad things are only those that divide the discriminant. And so it's a finite list. And all of the good primes are the ones not dividing discriminant. And this J is also very important because the A's and even the B's and the C's are not unique. You can sort of still rescale and get a change of variables that gives you effectively the same elliptic curve with a different equation. And so this J over an algebraically closed field is meant to detect whether or not two elliptic curves are the same. Two curves which are the same over an algebraically closed field may not, there may not be a nice rational transformation between them over Q itself, or over the field, a finite field, Fp over Fp squared. You might have to go to an extension before you find a map. And so that's all that's discussed in my in my typed notes, which I'm probably not going to have time for discussing. But that's it's still very important invariant to know, and one that's there's some important, especially if you're trying to compare things that aren't in Weierstrass form to Weierstrass form, because you want to know what curves in Weierstrass form you have that are equivalent to it. I'm just going to, so let's see, so if you have delta equals 0, and I'm going to go back to the case where we have the real numbers, the rational numbers, or complex numbers, because we can draw the elliptic curve in that case. Drawing an elliptic curve over a finite field isn't so exciting. Okay, so a couple things can happen when you have a discriminant being 0. You get, in any case, a singularity of some sort. And in Weierstrass form, you get this sort of thing, maybe, which is called a cusp. And so, in a way, you see there, so I mentioned at the beginning that the cubic on the right had to have distinct roots. So here we have the 3 roots being the same. We have a triple root. So this cusp is corresponding to a triple root. Well, guess what? The other case corresponds to a double root. And it's called a node, and it looks like this, kind of. You have 2 different slopes there at that point. So, technically speaking, we would say the slope at that point is not well defined unless you were to take a parametrization. So that's given by, say, that type of equation. And so this is an example of a node, or a tact node. And how do you detect a singularity aside from the discriminant? I mean, discriminant is the most useful thing for elliptic curves, but I mean, in order to come up with the concept of a discriminant for elliptic curves, you need to first know the definition of singularity to begin with. So that's discussed in my notes. I show you how to compute singularities. I show you can do it by differentiation, partial differentiation, if you want to check the singularity at infinity. You need to be able to do the partial differentiation to handle the z variable. And so that, I'm not going to do that out in right now, but you can look at the notes and see how to do that. But I want to mention now the curves that are used in cryptography. Okay, so there are what we call NIST curves. NIST is an organization. And this curves generally look like this. Y squared equals x cubed minus 3x plus b for some b. We're working over a finite field. B cannot be plus or minus 2 in order to get the discriminant condition to work out in the field, plus or minus 2 in the field. Characteristic must be different from 2 or 3. Okay. As you will see later at the end of my notes, and hopefully on the 4th day, I am not a fan of these curves. I consider them to be unsafe. So next, and much more interesting, are Koblitz curves. Y squared equals xy equals x cubed plus ax plus 1. A equals 0 or 1. But this is specifically in characteristic 2. So you're looking at some field that is has a power of 2 as the number of elements. And these curves are, I would say, without doubt, safer than this curves. Whether they are as safe as can be, I would say, is an open question. The Safe Curves website that I mentioned at the beginning does not include them for reasons I will make clear later. But the reasoning given there and in my notes is still somewhat conjectural. And so it can't be said unambiguously what the situation is there. Bernstein, the author of the Safe Curves website, and me, we believe that it's safer not to work in small characteristic. The prime should be big. And so that sort of automatically rules no. But they're still very interesting. There's a lot of good mathematics there that's worth discussing. The two which are sort of the heroes of these notes are the Montgomery curves so this is for A not equal to plus or minus 2, and this is for odd characteristic. Well, odd because you're working over a finite field, but I mean, it's a valid curve in characteristic 0, too. You're just not allowed to have characteristic 2. And Edwards curves. So far, all three of these that I have listed are in Weierstrass form. And these Edwards curves are not. And in fact, they are birational equivalent to Montgomery curves. And I show you explicitly in the type notes what the birational map is. I write it down exactly for you in the notes. And there's even a problem on it. But I don't think it's... So the thing is, we have... If you look up modern definitions of elliptic curves, often you'll see that they're defined to say that the elliptic curve is this projective curve genus 1 that's non-singular. That would seem to say that Edwards curves are not elliptic, but we have birational equivalence. I mean, the point is that you have this birational equivalence. Edwards curves are birational equivalent to a curve in Weierstrass form, which is non-singular. And so, from a modern perspective, we kind of like our elliptic curves equations to be non-singular, and that's great for most theoretical purposes in number theory. But these Edwards curves turn out to be very useful in cryptography. And so it's sort of a bit surprising, actually, I think, that here's this curve. It's singular. It has singularities, which I ask you to detect in one of the exercises. And yet, it's still, in some ways, a better model for elliptic curve in cryptography than Montgomery curves, largely because of the very symmetric addition law. Okay, so I have a little bit of time left to start finite fields. Are there any questions in what I've been going over so far for elliptic curves stuff? Because I'm now going to be sort of switching gears here to finite fields. Okay, so finite fields.
There is only about a couple minutes left in my clock.
Well, that clock says 7. Should I go by that clock or what?
It's about up to 3:50 your lecture.
Oh, 3:50. Only 2.
Yes, 50.
So I'm already over. All right. So I guess finite fields will start next time. That's fine. Any questions at all? All right. If you want help installing Sage, you can come find someone.